Alright, CUET fighters. You've been grinding away, you know your rate laws inside and out, right? But what if I told you there's one type of question, a question that looks so simple that examiners absolutely love to use? It's their favorite little trick to tell the top rankers from the rest of the pack. Well, today, we're not just going to learn about that trap, we're going to take it apart, piece by piece, so you'll spot it instantly on exam day.
Okay, take a look at this. Simple, right? Hydrolysis of ethyl acetate. You see two reactants here, the ethyl acetate and water. So your brain, what does it do? It goes reactant A plus reactant B, that's got to be second order. You're probably nodding your head right now thinking, yep, second order, next question. Am I right?
And bam, that's the trap. It's not second order. And if you thought it was, don't worry. You've just done exactly what the question designer wanted you to do. You walked right into their little trap.
And look, this isn't just about getting a question wrong. This is about that -1 mark, the one that can drop your rank by hundreds, maybe even thousands. It looks like a second-order reaction, it feels like one, but it's not. So, what's the deal? Here's the thing. There is one secret condition hidden in this reaction that changes everything. And I promise you, by the time we're done here, you're going to know exactly what that secret is.
All right, let's dive into this classic CUET trap. To beat it, you gotta know how it works.
Okay, first things first. I need a total attention reset from you right now. Forget the balanced equation for a second. Seriously, the number one mistake, the thing that catches almost everyone, is just counting the reactants on the page. But the real secret, the key to cracking these questions, it's not in the reaction itself. It's hidden in the conditions under which the reaction is happening.
And that brings us to the name of the game, the pseudo first-order reaction. Pseudo just means fake, right? It's like a disguise. This is a reaction that is, deep down, a second-order reaction, but it's putting on a costume, pretending to be first-order. And the whole reason it can pull off this disguise is because of that one crucial phrase: one of the reactants is in vast excess.
So how does this vast excess thing actually work? How does it create this illusion? Let's uncover the secret. Check this out. This is the magic trick right here. On the left, you've got the real rate law. Rate equals K times concentration of A times concentration of B. It depends on two things. But now, imagine reactant B is the entire ocean, and reactant A is just a single drop of ink. As the reaction goes on, that drop of ink disappears, right? Its concentration changes a lot. But the ocean? Does the ocean's concentration change? Barely at all. It's effectively constant. And that's why, on the right, it looks like the rate only depends on A, our little drop of ink.
So you might be asking, where did the concentration of B go in the new equation? Well, it didn't just vanish. Since its concentration is basically a constant number, we lump it in with the other constant K. We multiply them together and create a new constant, which we call K prime. So K prime is just a combination of the old K and the massive, unchanging concentration of B. It's a clever mathematical sleight of hand.
All right, let's pause here. Time for a pause and think moment. I really want you to think this through. Based on what we just said, if we keep our main reactant A the same, but we double the amount of our excess reactant B, what do you think happens to the reaction rate? Go on, hit pause, give it a thought.
Okay, hope you gave that some thought. So that's the theory. But how do we actually use this on the exam? Let's hack the rate law and look at the math you'll need when you're under pressure.
And I've got some great news for you. This is the best part. You do not need to learn a whole new set of equations for this. Nope, because the reaction is pretending to be first order, we can treat it like one. You're going to use the exact same integrated rate laws and half-life formulas that you already know for any other first-order reaction. See? Look familiar? Of course they do. The integrated rate law, the half-life equation, you've got these memorized. The only, and I mean only difference, is that instead of K, you're using our new friend, K prime. And notice something really important. The half-life is still independent of the starting concentration of our main reactant. That's a classic hallmark of a first-order reaction.
Okay, time to put this to the test. Here is a mini MCQ challenge for you. This is a classic CUET-style question. If we double the concentration of the excess reactant, what happens to our apparent rate constant K prime? Does it get cut in half, stay the same, or double? Pause. Lock in your answer, A, B, or C.
And the answer is C. It doubles. Why? Just think back to the formula. K prime equals K times the concentration of B. So if you double B, you have to double K prime. They are directly linked. Seriously, star this in your notes. This is an A+ conceptual question they absolutely love to throw at you.
Okay, so you get the theory, you get the math, but now for the million-dollar question. How do you spot one of these in the wild when you're in the exam and the clock is ticking?
All right, time for our second attention reset. I want you to change your mindset. For just a minute, stop thinking like a student. I want you to think like the examiner. If you were writing this test, how would you disguise this concept to make it tricky? You wouldn't say, this is a pseudo first-order reaction, right? No way. You'd hide the clues somewhere subtle.
So let's go all the way back to the first question I asked you, the hydrolysis of ethyl acetate. Let's break it down like an examiner. Step 1. What are the reactants? Easy. Ethyl acetate and water. Step 2. What's the hidden clue? What are the conditions? The reaction is hydrolysis. It's happening in water. That means water isn't just a reactant, it's the solvent. It's the ocean. It's in vast excess. And that's the giveaway. So step 3, you conclude. The rate really only depends on the ethyl acetate. Bingo. It's a pseudo first-order reaction.
And they do it again with this classic, the inversion of cane sugar. It's the exact same pattern. Check it out. Step 1, reactants, sucrose and water. Step 2, the condition, again, it's hydrolysis in water, so water's the solvent, it's in vast excess. Step 3, the conclusion, the rate only cares about the sucrose concentration. You see the pattern? I want you to burn this into your brain. If water is a reactant and the solvent, a little alarm bell should go off in your head that says, hey, this might be a pseudo first-order trap.
All right, let's bring it all home. We're going to do a quick rank booster recap to make sure all of this sticks.
Okay, remember at the very beginning, I told you there was one secret condition that changes everything. Well, here it is. We're closing that loop. The big secret is just this. One reactant is present in a huge, massive, overwhelming excess. That's it. That's the whole magic trick. Its concentration is so big that it basically doesn't change.
So, here are your key takeaways for exam day. Number 1, always look for a reactant in large excess. Water as a solvent is the biggest red flag. 2, remember, the reaction will behave like it's first order. 3, you use the standard first-order equations you already know, just with K prime instead of K. And 4, and this is the expert-level tip, remember that K prime isn't a true constant. It depends on the concentration of that excess reactant. So there you have it. You've now officially cracked one of the slickest traps in chemical kinetics. But the real takeaway here isn't just about this one reaction type. It's about learning to think critically and look for those hidden conditions. So I'll leave you with this question. Now that you know how to spot this kind of trap, what other simple concepts in chemistry might be hiding a deeper, rank-boosting secret? That's the mindset of a top performer. Keep digging.